Work is done by a force whenever that force itself is the cause of a motion, and we can find the amount of work done by multiplying the size of the force with the displacement in the direction the force acts. In this case, you can have a force F, and we're going to displace it through a distance S. Distance S will be represented by the x-axis, and the size of the force will be represented in the y-axis. So if the force is constant, we're applying it through distance S, then the force along the y-axis should not be changing through distance S. So let's do a little bit of work by this force, by applying the force through a small distance S. In this case, we applied the size of the force, which we quantified as this value on the y-axis, and we applied it through a very small distance S. The amount of work done, of course, is equal to F times S, and you will notice that this is also equal to the area under the graph, the shaded blue area. Now if we keep applying that force, that same constant force, through a greater and greater and greater distance, we can see that we do more and more and more work. And in all cases, as we apply the force, the amount of work done is given by the area under the graph. The calculation would be very easy if the force were constant and the displacement were known, because the area under the graph is found by F times S. The question is, how about if the force is varying? It does not start at a fixed value and remain at that throughout. It will be very difficult then to use F times S to find the work done. What we need to do in that case is to find the area under the graph, even though the force may be variable. When a force is used to either compress or stretch a spring, then that force is a cause of a displacement, and therefore work is done on the spring, so energy is stored in the spring. But how much energy is stored? Well, when we first start compressing or stretching the spring, we don't need very much force. We start with no force, and then we gradually apply a larger force, and that larger force causes a specific extension. We then increase the force, we cause further extension. Increase the force further, and we get further extension. And this happens, of course, in very, very small steps of increasing an extension until we've applied the force that we wanted to and achieved the extension that we wanted to. So how much work have we done, or how much energy is actually stored in the spring? Well, when the spring is released, it can exert this force as the displacement reduces, and therefore the area under the graph, or representing the average force times the displacement, is the work done. Note that this is given by a half times the maximum force, F, multiplied by the displacement that was actually caused by the application of the maximum force. What happens if the force that was applied was not constant at all, or did not start from zero and increase gradually to a specific value, but let's say started from a particular value and then increased, but then increased at a different rate all the time, and then perhaps decreased, but still caused a displacement all the time until about there, let's say. What would be the work done by this variable force to cause this displacement? Well, in this case, a single calculation will be very difficult. But in this case, the work done by this variable force to extend the spring by this displacement will be equal to the area under the graph. And we can quite easily find that by either counting the squares and multiplying by the area of each square. Or we could draw a line to approximate the area under the graph into a regular shape, whose area, the area of the regular shape, would be actually equal to the area under the graph. We do this by drawing a straight line. We now have a regular shape. And so the white areas that we counted in the shape of the regular, the area of the regular shape, these white areas, must be equal to the green areas that we should have counted, which we did not. So we get a rough estimation of the area under the graph.